In this exercise, we are going to find out whether a system is ill-conditioned or not. An ill-conditioned system means that the solution of the system is sensitive to round-off errors. When you round off a number in a matrix, the outcome can become totally different. Let's take the following system as an example for this ill-conditioned system to illustrate what it actually means. In this system, we have a value a, which has an approximate value of 400.5. Depending on the actual value of a, you can round off a to 400 or to 401. If you solve this system for a is 400, you will get as an answer that x is minus 100 and y is minus 200. However, when you solve the system for a is 401, you will get as an answer that x is 40,000 and y is 79,800. This is a factor of around 4,000 difference. So, depending on how you round off a, you get a completely different outcome. Therefore, this system is ill-conditioned, because such a small difference in a. In this exercise, so we need to construct a matrix of n by n, where each position has the following value. How do we construct such a matrix? If we look at the position numbers of the value in the matrix, we see that they are, of course, sequential. When we want to fill the matrix, it would be easiest to walk through the matrix and give each position the right value. So we first do the first row, then the second row, then the third row, etc. Since we are going to walk through the matrix, we can use a loop. We know how many values there are in the matrix, so we can use a for loop. The only challenging part here is that the for loop has to be in 2D, since we want to cover all the values of I, but also all the values of j. Let's write down what we want to do. Let's say we want to cover each row from left to right. So we start at I as 1, and we have to cover all values of j. Then we go to I as 2, and again cover all values of j. Then we go to I as 3, and again cover all values of j. We keep repeating this until we have covered the whole matrix. As you see, we loop through all the values of I, and for each I, we loop through all the values of j. There's a useful trick that you can use in MATLAB to do this, and it's called the nested for loop, which is basically a for loop in a for loop. So first you define the for loop for I to n, and then you define the for loop for j to n. Then in the core of this nested for loop you type whatever you want to do, and then close both with an end. So what happens now? So first of all I is 1, and then we move into the for loop of j. This means we loop through all values of j until we are done, then I becomes 2. Again, we loop through all the values of j until we are done here again, then I becomes 3. Then we loop through all the values of j again. This keeps going on until we reach I as n, and we again loop through all the values of j. This way you have covered all the values of the matrix from top to bottom and from left to right. So now we know how to construct a Hilbert matrix with the nested for loop. Let's do that in MATLAB. First of all, let's take 5 for n and then construct an empty matrix of n by n that we are going to fill up. Then we define the nested for loop, close them with an end, and then in the core of the loop we can define the Hilbert matrix with the formula that was given in the exercise. Then in the end display the matrix, and now when we run it, we get the Hilbert matrix, and you can see that there's a lot of numbers that are prone to round-off errors, so you can already see why this could be an ill-conditioned matrix. Now we have constructed the Hilbert matrix, we can determine whether it is ill-conditioned. First we are asked to calculate a to the power of minus 1 times a. This is basically the same as dividing a by a. The expected outcome therefore should be 1. However, since we are calculating with matrices, we don't get a single number as an output, but a matrix. This matrix is the size of the multiplied matrices and consists of zeros and a diagonal of 1s. This matrix is the matrix version of 1, and if you multiply it with something, it's the same as multiplying by 1. This matrix is called the identity matrix. So, a to the power of -1 times a, and also the other way around, should result in the identity matrix. However, this only goes for well-conditioned systems. This means that we can determine whether a matrix is well-conditioned by calculating the identity matrix. Another way to determine whether your system is well-conditioned is to calculate the condition number. The larger this number is, the more ill-defined your system is. So a lower condition number. Once we have calculated, so let's try this first in MATLAB for n is 4. Now back to MATLAB. First n is 4. And let's call it capital A, that's easier. Then construct the first identity matrix and the second identity matrix. And the condition number can be calculated with the function cond. Then we don't want to display the matrix, we want to plot the identity matrices. Let's plot them in subplots, a subplot of 1 by 2. Furthermore, let's add the condition number to the title of the plots, also along with the n, so we can see the impact of n on the condition number. Now we only use one n, but later on we will use more. So now we can plot. And we cannot really reach something from these plots because we don't have a color bar, so let's add that. We can just type color bar. And now we do have plots that we can use. So what do we see here? Basically, these two plots are just visualizations of the matrix, of the identity matrices you just have constructed. So each little block in this image represents one number in your identity matrix. And as you can see, yellow corresponds to 1 and dark blue corresponds to 0. So this is actually a good identity matrix. So from this figure you can see that at NS4 the Hilbert matrix still is quite well defined, though the condition number is already a little high. For visualizing and comparing our results, it would be nice to not do this calculation for just one n, but for different n's of different sizes. Therefore, let's build a for loop around our code so we can calculate with different n's at a time and compare the results. So let's transform the code in such a way that we can loop through n. First, we have to make a vector of the n's. Let's call it differently because then we don't override variables. So we want to do 4, 10, and 20. And then they will say for, let's say k is the length of the n vector, and close it with an end. Then n becomes that value of the n vector. The rest of the code does not need alteration until we get at the plots, because now we have to make subplots using indices, and this is quite challenging sometimes. So let's look into a bit more detail how to do this. We have 3 n's, and for each n it would be nice to plot both identity matrices so we can really compare the results. This brings us to a total of 6 plots. If we can use the indices, so basically the number of the calculation that you're in, so we are going to do 3 calculations, so the index of the first calculation is 1, of the second is 2, and of the third one is 3. If we can use those to appoint a place in the subplot to a graph, it would be great. In this case, the index is k, so we are going to use k as 1, k as 2, and k as 3 to get the graphs in the right place of the subplot. So let's look at the subplot function, how we can do this. The subplot has 3 inputs: the amount of rows of the subplot, the amount of columns, and the plot number. So basically the position within the subplot where the graph has to be. In our case, we have 3 rows, which corresponds to the amount of n's, actually. So in this case, the length of the n vector. The amount of columns is 2, because we want to plot the 2 identity matrices. And then lastly, the plot number can be either 1, 2, 3, 4, 5, or 6. So how do we kind of write a formula that determines whether your plot number is the right one? For case 1, we have plot numbers 1 and 2. For case 2, we have plots 3 and 4. And for case 3, we have plots 5 and 6. There's not really one way to do this in one subplot command because you have 1 input number and 2 output numbers, so we have to write 2 different subplot functions. We see that for the 2, 4, and 6, it's easy because this plot number is just 2 times the value of k. Then for the other 3 subplots, the value is 2 times k minus 1. So by making 2 subplot functions and at the place of the plot number, put these 2 formulas, we can automatically plot the figures in the right position within the subplot. Let's put these subplot function into MATLAB. So the amount of rows is the length of the vector. Then the plot number is, for the first case, k times 2 minus 1. And then we can copy that for the second subplot and just change the formula because there the plot number is k times 2. So now when we plot it, we have 6 nice graphs that we can compare to each other. For n is 4, the identity matrix is still recognizable and the condition number is high, but not super high. But when you look at the graphs of n is 10 and n is 20, you see that the condition number is huge and that also the graphs don't even remotely look like an identity matrix anymore. And this is all because of the ill-defined Hilbert matrix that when you multiply it with each other, apparently the round of errors are so large that it completely changes the output matrix. Let's see if we can prevent these round of errors. Until now, we have always calculated with numbers. However, MATLAB can also calculate symbolically, which means that MATLAB first uses MUPAT software to calculate the solution algebraically, so with symbols. And then in the final step of the calculation, it replaces the symbol with numbers. This prevents round of errors in your calculations, but it's not suitable for every calculation there is. In this exercise, we are going to calculate x from the formula ax is b. Usually you would just divide b by a, but it doesn't work that way with matrices, so we have a special operation. You can either use x is a backslash b, or x is the inverse of a times b. We will try this both symbolically and numerically. So we have our code again. Let's turn off the plot because it only slows things down. Furthermore, let's define b, which is a column vector of 1s, so 1's n by 1. And then we can calculate x using x is a backslash b. We also want to do this symbolically. So we can do this by defining a new a and defining it as a symbol of the numerical a, and doing the same for b, and then we can calculate the symbolic x in the same way we calculated the numerical x. Then let's add a display function here to show for which n we get which x. We can also do this for the symbolic function, just copy paste. And now we run it and we get an error in line 28. Oh, we need to insert a space there between the string and the num to string. Run it again. Yes, now we get an output. If we now compare these numbers, we see that the numerical outcome has a lot more decimal numbers than the symbolic outcome. Basically, the symbolic outcome doesn't have decimal numbers and the numerical does. We can look into this in a bit more detail if we type format long, because then MATLAB will type all decimals. And now indeed you see that there's a lot of decimals that are really close to 0.999, so really prone to round off errors. And probably from this you can expect that a symbolically solved matrix is far more well-conditioned than a numerically solved matrix. We can check this again by calculating the condition number and plotting the identity matrices of the symbolic Hilbert matrix. So let's copy paste everything from our previous script and make everything symbolical. And let's turn on the plots again, and let's make a second plot for the symbolic solution so we can compare the numerical and the symbolic solution to each other. So now everything is in place. Let's run it. And we get an error. Input to num2string must be numeric. Of course, if you want to plot something or put it into num2string, you need a numeric input. And we now have symbolic inputs. So we can change this by typing double around the symbolic values to convert it into a numerical value. And now we see that the code is running. And now the figures are done. We can compare them with each other. And we see that indeed the symbolic solution of the Hilbert matrix results in a nice identity matrix each time. Whereas when you use the numerical solution, you see that the identity matrix becomes some blur. So indeed, in this case, solving this system symbolically results into a well-defined system, whereas when we solve it numerically, we have an ill-defined system. There's also something else that can contribute to the errors in your system. I previously mentioned that there are two ways to calculate x. Let's see which one is more robust. In this exercise, we assume that we know that A is a Hilbert matrix of 10 by 10. Furthermore, we also know x, it's a vector of 1s. Now, using A and x, we can calculate B. Now we know the solution to all variables. Now, with the B we just calculated, we can calculate x again. The new x and the given x are supposed to be the same, because they were calculated using the same A and B. Well, spoiler alert, they are not. There's always an error in this calculation. Therefore, by subtracting x from the calculated x, we can calculate the error of the two and see which one of the methods is best to calculate. Also, remember that we can rewrite these two formulas again to ax is b, and then to ax minus b is 0. Therefore, you would expect that when we use our new x1 and x2 in these formulas, we would get 0. Again, this is not the case. The number we get is the residual, the margin in which x varies from the actual x. With the error and the residual, we can calculate which method is best. Let's also take into account which method is fastest, because this is also sometimes important in coding. Okay, so let's open our favorite calculator, MATLAB again, and define everything we know. So n is 10, x is a vector of 1s of the size n, A is the Hilbert matrix. We can copy this from the previous code. Oh, oops, x has to be 1s, of course. And now we can calculate x1. Oops, don't forget to define b, because we need that. Then calculate x1. We will define x1 using the backslash method, and then we can calculate the error that this method gives and the residual that this method gives. Let's also count the time that this method takes using tick and tock. And then the second method will be the inverse method. So let's settle the battle once and for all. We have run it and we can now see the results. Let's first check the first method, which was the backslash method. Here we see that the error is in the range of 10 to the power of minus 3, and the residual is in the range of 10 to the power of minus 15, which is really low, and the elapsed time is 0.0008 seconds. Then for the second method, the inverse method, it took longer, and also the error is in the range of 10 to the power of 5, and the residual as well. So these results are not as far as good as the backslash method. So also the backslash method was way faster. So this is not definitive, because in some cases one works better than the other. But for this case, for this ill-defined system, we have shown that the backslash method is the best one to use.